Welcome to my channel, Meaninig. Friends, we learn here the meaning of NMR, nuclear magnetic resonance. Everyone know the first spectroscopy got a Nobel Prize in 1952 to the both scientists, that is Felix Bloch and Edward Purcell. They are working in a subject physics. But before that, the work will be done by the star. These two scientists, one is given, that is Purcell is given the NMR for a paraffin, while the Bloch is given the NMR for a ethanol molecule. Okay, three type of the hydrogens of ethanol will be observed here. As I said, the nuclear magnetic moment will be detected by Stern using a molecular beam in 1932. Today, everyone know this NMR actually a absorption of light and due absorption of light due to a nuclear spin orientation. Now today we have to learn the actual meaning of that NMR, how the nuclear spin is there, what is actually the magnetic field will be generated there, that is the radio frequency will be we are going to apply um, and how the resonance will be occur. Now if you look in a nuclei, the nuclei is having the one of the property, and this property is known as a spin. And if the nuclei is going to behave if they were spinning, actually I have put a word, we don't know if they actually do spin, but we are going to assume they are spinning, and if they are spinning they must having the properties like an electron which has the two spin, that is plus up and minus up. And if the spin active nucleus this is having a quantum number, and this called as a spin quantum number I will be there. Now according to that we can calculate the number of allowed spin state. I is a physical constant that we called as a spin quantum number. Okay, now those having the I value, they are easily show the a spinning or they are NMR active. And now we have to look which atom or element or molecule are NMR active. So that the first we say any atom or element which having an odd number of electron. But I say this having the odd number of electron, and if they are having odd number of electrons will be there, then and then we say these nuclei will be a NMR active. This is very important. This must have the odd number of the neutrons or odd number of the protons, and if both are odd then we say they are NMR active will be there. In addition with that we can also say, because neutron according to this neutron and protons, we can easily say that the atomic nuclei as well as atomic number as well as atomic mass number. And according to that, we say the nuclei must possess odd atomic number or odd mass number or both are odd. For that, we are going to consider the molecules. Here we have the hydrogen, it's having the atomic number 1 and a mass number is 1. So that both are odd, it is NMR active one, as it has a 1 proton and no neutron. And if you look another one molecule, that is the carbon molecule. The carbon, which is if you take that is the atomic number will be the 6 and its mass number is a 12. What is there? In a both atomic number as well as mass numbers are the odd, and due to presence of the atomic number and mass number are odd, as well as it has 6 proton and 6 neutrons, this C12 isotope of the carbon does not going to show NMR or does not show the NMR signal. Though if you look, the its another isotope, that is C613. What is their mass number is here odd one, and it having the 7 neutrons, so that due to the odd things, the C13 will be a NMR active one. Likewise, we can consider another one molecule, that is the P31. Okay, in the P31 there is a 15 protons and 16 neutrons. Okay, 15, this is odd number or atomic number is 15, and 31 neutron mass number is also odd one, so that it is also a NMR active one. And if you look the chlorine 919, this is also a NMR active, because it is also having a both number are the odd one. So these are active molecules in a NMR will be there. If you look the another one example, that is the oxygen. Oxygen everyone know. Okay, oxygen is having the atomic number will be the 8, and that of mass number will be the 16. What is there in the oxygen? Both are even, so that the oxygen 16 does not going to obey a nuclear spin or does not having a nuclear spin. Its I value will be the 0. Everyone know about the chlorine again. If you look the chlorine, like the halogen family, it is having the atomic number will be the 17, and mass number will be the 35 or its isotope 37. Both are odd, so it is a NMR active molecules. And as they are NMR active one, we can easily calculate the nuclear spin quantum, allowed number of spin quantum, the spin state will be there depending upon its spin quantum number. And what is the actual formula for this one? The formula for the such compounds will be a 2Ni plus 1. Everyone know the formula. And when we are going to use 2Ni plus 1 will be the formula to calculate number of allowed spin state, where this n is stands for the number of atoms. Okay, 2Ni plus 1. Now we can look for a simple example, hydrogen. Hydrogen is having the I value will be the half. Okay, how much I value for the hydrogen is a 1.5. Only half is there, 1 by 2. So that if you put in the equation, what to get, hydrogen atom is single atom, 2 into 1, 2 into half, it's become 1 plus 1. That means number of allowed spin state for the hydrogens are 2 spin state. Okay, nuclear spin state, number of allowed spin state are the 2 1. Likewise, if you look for the C13, it is also having the I value will be the half. Okay, both C13 and the H1 is having the I value will be the half one. So number of allowed spin states are again 2 will be there. Okay, number of allowed spin states are the 2 will be there. Then if you look for the phosphorus 31, this is also having the I value will be the half. So number of allowed spin states are again 2 will be there. And if you look for the fluorine, this is also having the I value will be the half will be there. Okay, all these examples are having the I value, nuclear spin quantum number will be the half. But are they half for each and every atom? No, they are not half. There may be a 3 by 2 will be there. For which atoms? We have taken another one examples, that is chlorine 35, and this chlorine 35 is belongs to the I value will be a 3 by 2. What is there? The chlorine as having the I value will be the 3 by 2. Then we are going to calculate number of allowed spin states for this one. 3 into 1 into 2, 6 divided by 2 is 3 plus 1. That means we got here the value will be the 4 1. Okay, for chlorine the number of allowed spin states are 4 1. And if you look for the another one isotope, that is oxygen 17. This oxygen 17 is having the I value will be the 5 by 2 is there. Oxygen atom is having the 5 by 2, and when you are going to put the value 5 by 2, 5 into 1 into 2, 10 divided by 2, 5 plus 1, 6. That means oxygen 17 is having the number of allowed spin states are 6 1. Okay, this is the simple idea about the nucleus. Okay, nucleus, because nucleus is having the property of the spinning, and due to the spinning property where those nuclei is having odd number of atomic mass or atomic number, these are only show the spinning. Other nuclei does not going to show spinning like your even mass or even atomic number. Okay, this is the first nuclear. Now we have to go for the second, that is the magnetic. For that we have to consider for the a simple spinning protons will be there, and this spinning proton, they are behave like a mini magnet. Because what happened, uh, the spin state of an nuclei is not does not having the same energy or equivalent energy when you are going to apply the external magnetic field to it. Okay, the nuclei is going to spin around its own axis, so that due to the spinning motion they are going to generate a magnetic field. But these magnetic field are very less. Okay, if you look uh, in a small way, as compared to applied magnetic field, the magnetic field generated by the spinning is very less. But uh, we have to look for the molecular level, and due to the molecular levels we can say that the magnetic moment will be also important for shielding will be there. So that we have to consider the magnetic moment which is generated by the spinning motion. That means nuclei will be going to spin around its own axis, so it creates a magnetic field. And so, due to the creation of magnetic field, it is behave like a mini magnet will be there. Then what happened? Let's consider if we are going to put these nuclei in a applied magnetic field. Okay, if you are going to apply the magnetic field in these directions, okay, magnetic field will be denoted by the applied magnetic field will be denoted by the b0. And when you are going to apply the magnetic field, uh, the nuclei will be having the spinning directions. Okay, and according to that we can show positive spin and negative spin. Okay, actually some people say that clockwise means half spin, anti-clockwise means minus spin. It is not that. The when the nuclei is having the spinning in the same direction of applied magnetic field, then they are present in a parallel fashions. Okay, this is a applied magnetic field spin, and this is a nuclei spin. Both are going to show in a one direction or unidirectional, and when they are unidirectional we say parallel, and then that time the spin will be called as a positive spin. Okay, this spin will be called as a positive spin, and we say as a half spin for the nucleus. So here will be the plus halves will be there, and we call as a up spin for the half spin. And it has a less energy. Why it has less energy? Because when you look for the applied magnetic field direction, and nuclei will be spinning in opposite direction, and when it is going to oppose in a moves in opposite direction, its magnetic field opposes to the applied magnetic field, so that there is an increase in a energy will be there, and this fashion will be a unaligned or anti-parallel. Okay, this is the applied magnetic fields and direction of the spinning of nuclei will be the opposite. Okay, then it is a unparallel will be there, and the spin will be shown by the negative charge, and we put minus half to the this one. Okay, so it is behave like a nuclei, and due to that, what happened? The if you look consider a simple a nuclei, that is hydrogen nuclei, then what happened? The hydrogen nuclei is going to adopt its orientation with respect to the applied magnetic field in an aligned fashion or in a unaligned fashion, as it has a two spin, plus half spin and the minus half spin will be there, and they will be differentiated by the some amount of the energy when we are going to apply an external magnetic field. In a aligned, there is a less energy, while in unaligned, there is a more energy due to opposing to the applied magnetic field is there. Now, this is the about the second what, that is the magnetic field, and due to the spinning of a nuclei, it creates its own magnetic field. There is a therefore the second what will be the magnetic will be there, and we are going to put the same atom in a secondary magnetic field, so the these two magnetic field are going to couple, so that there is a what will be the magnetic. And now we have to move towards the its third what, that is a resonance. And for that we have to look the how absorption of energy will be taking place. All of you know, when if you take any nuclei, and this nuclei will be present in a aligned fashion to an applied magnetic field, now it is going to absorb an energy, and when it is going to absorb an energy, it change its spin and it goes to the opposite spin with respect to the applied field will be there. And now we say this is a quantized process, and this in the quantized process energy must be absorbed, and which is equal to there is a energy difference between these two states we call as a lower state and the higher state. Then in applied, h mu amount of energy will be applied here. Okay, and as the h mu amount of energy will be going to apply, how much amount of magnetic field we are to apply to change the spin state of the nuclei, we are going to calculate. Now so that we say the energy difference is actually a functions of an applied magnetic field. Okay, functions of B0, applied magnetic field. When we apply more magnetic field, the energy difference is more. When you apply a lower magnetic field, the energy difference will be the less one. Now, the magnetic this energy level separation is also, it depends upon a particular nuclei. How the particular nuclei? If you consider there is a hydrogen nuclei or there is a carbon nuclei, and this nuclei is having a specific a special ratio. We call this ratio as a gamma. What is the ratio for the gamma will be there? There is a ratio of magnetic moment. What I said? There is a ratio of magnetic moment to a ratio of another moment, that is called as a angular moment. Okay, this two moment ratio, that is magnetic moment and angular moment, this ratio is known as a magnetogyric ratio or gyromagnetic ratio, and it is a different because each nuclei is having the different charge and mass, so that we are going to put in the same equation. Okay, therefore we say delta E is now becomes a function of gamma and B0. Okay, gamma B0. Now this gamma is a constant one. and as gamma will be the constant, uh, we can put out from the functions, uh, and all of you know this gamma will be a ratio of magnetic moment to the angular moment. This gamma is a quantized process, and it is going to quantized by the unit of h upon 2 pi. Okay, therefore we are going to put gamma h upon 2 pi, and functions of b0 we are going to solve, and it is depends upon b0, and we know amount of energy will be applied is a h mu amount of energy will be there. So that what happen in these equations, we are going to cancels h and h, and now we get the simple equations for the molecule. How much amount of energy mu is equal to gamma, which is a constant, then applied magnetic field B0 divided by 2 pi. So that from these equations we are going to rearrange and calculate the how much amount of magnetic field we are going to apply for an to do the change of the spin state from lower to the higher one. And as the spin state will be going to change. When the spin state will be going to change, or how much amount of energy, we can calculate the B0. Okay, and when the B0 will be applied to the any nuclei, we say h mu amount of energy B0, and according to the applied magnetic field, the nuclei will be going to spinning along their own axis. At the same time, if you put in a secondary magnetic field, it creates a angular momentum, and due to the this angular path, it will be creates a secondary magnetic field. And this secondary magnetic field is uh, given in the form of frequency. This is called as a omega, and this omega is known as a Larmor frequency or precision frequency, or it is called as a resonance frequency. And when this applied frequency mu and omega are becomes equal, at that time what happens? The spin of the nuclei is in a aligned fashions, will be goes to the opposing fashions. When there is a mu which equal to becomes a omega. Okay, mu is equal to becomes the omega. That times that means applied frequency and Larmor frequency or resonating frequency become equal, the spin state will be occur, and this condition is known as a resonance. This is a meaning of NMR. Nuclear, we have selected nuclei, those are having the spinning property. Due to the spinning, it will be show magnetic field, and magnetic creates magnetic field of its own. We are going to apply external magnetic field, therefore the word will be the magnetic, and it is going to show change in the spin state. The condition is known as condition is called as the resonance. This is the meaning of 3 word NMR. Okay, thank you. If you are new to my channel, kindly subscribe, share and like. Thank you.